So the first section of our sheet tells us that we have two different classes of molecules. We have the class 1 and the class 2. Now, what they are is they all are carbonyl. Remember, this is a carbonyl group. And there are many, many different types of carbonyls. Now, we can organize them in two different groups, class 1 and class 2. Now, for class 1, the way it works is, what we're looking at is any time a carbonyl is so we care about this right here, like what's on the right side. And it really doesn't matter right or left because you could flip it. But we know for sure that one side of the carbonyl is allowed to have a carbon or an H. That's always given. But it's the other side, Z, that we care about. So this is the one that's going to define what the molecule actually is. So it turns out if you have an H on both sides of a carbonyl, that's the simplest carbonyl, formaldehyde. Okay? It's an aldehyde. But aldehydes extend beyond two H's, right? You can have a carbon on one side, and then an H on the other has to have an H, so it's a terminal carbonyl. It's on an end because it has an H on at least one side, and so that's an aldehyde. And then a ketone has the R that we're allowed to have on one side and an R on the other side. Okay, so if you have carbon on both sides of a carbonyl, then it's a ketone. These are all class 1 molecules. And the reason why they're class 1, what makes them similar, is that the atom on the right, the Z group, is either something that's less electronegative than carbon, hydrogen, or equal electronegative to carbon, carbon. And so that's what makes it class 1. Now, the class 2 molecules, there's a whole bunch, and I limited to just a few here that I felt were important for this exam. Next semester, you'll learn a bunch more, but for now, this is good. Now, what makes class 2 carbonyls, is that the Z group is an atom that's more electronegative than carbon. So what we say is that this Z group is a leaving group, okay? And we'll see in its reaction concept that you have a leaving group here. So the first one is a halogen. If it's Cl, Br, I, or F, it's called an acyl halide. And that's a class 1. And notice how this is increasing reactivity. So it shows you the trend of reactivity. Acyl halides are the most reactive class 2 compounds. Then you have acid anhydride. So you have this carbonyl that has another carbonyl attached to it, but it's flanked by an oxygen. There's an oxygen in the middle between them. That's an acid anhydride. An ester is an OR. And so any kind of carbon after that O is fine. That's an ester. And a carboxylic acid, we all know, is OH. Now, actually, these bottom two, are actually equal in reactivity. They're equal in reactivity. So even though this is a trend going up, these two are actually the same. I just put it below, but they're equal to each other. All right, so this is the trend. And what we have here is some rules about reactivity. Now remember, the idea here is that when you have a carbonyl, that it's partial positive here and partial negative up there. So what we want to figure out is, when is it good for a nucleophile to get into this carbon? Because that's what has to happen. We need to bring a nucleophile into that position, and in order to do that, we need that carbon to be positive, right? Because what does a nucleophile look for? It looks for positive species, right? So the more positive the carbon's going to be, then the more likely a nucleophile will go in there. And we found there are two trends that interfere with this logic, or that will increase or decrease the positivity of our carbon. And that is, the first one has to do with steric. We were told that when you have branching, like R groups on both sides, that they create electronic clouds. And these clouds are going to interfere when a nucleophile tries to get into that carbon. Those yellow electronic clouds are going to be repelling the nucleophile's electronic cloud. And so it's best if we have no carbons around that carbonyl, because it's less hindered that way. Okay? And so that's why ketones are not as reactive as aldehydes. And we see that ketones are at the bottom of our list. Now, a carbon that has an aldehyde form, a carbonyl with an aldehyde form, well, if it has one R group, then it's going to have some repulsion, right? That's going to give it some steric crowding. And so that's not as bad as a ketone, but it's not as good as a formaldehyde. Formaldehydes have virtually no crowding around its carbonyl. So it's very easy for a nucleophile to get in. Now, we were told that that's the idea of the steric issue, the steric hindrance. But the second one has to do with the positivity of the carbonyl. So another idea that we discussed is what we call electronic factors, electronic issues. Well, actually, maybe not even necessarily an issue, so let's say electronic. And remember, there are three types. There's hyperconjugation, which is the stabilization by having a neighbor orbital come close to the carbon that's positive. Okay, there's inductive effects, or induction. And then there's resonance, which is always the best of all. Resonance is the most stabilizing. So a ketone will have two carbons that are surrounding the carbonyl. So this positive here is not so bad with ketone, because ketone carbons are going to help out by giving electrons to the positive carbon. And it does it two ways. It could do it through hyperconjugation, and it can do it through inductivity, right? So we could move electrons in the single bond towards carbonyl, like that. That's inductivity. But also the orbitals of these H's that are attached to carbon next door can push its electrons over to the positive carbon, and that's called hyperconjugation. So we have inductive and hyperconjugation stabilization. But the one thing ketones do not have is they have no resonance stabilization. Okay? So, stabilization. There you go. So it has no resonance stabilization. Ketones have no resonance stabilization. Now, aldehydes, they have no inductivity. They have no hyperconjugation, and they have no resonance stabilization. So aldehyde, like formaldehyde, this is for formaldehyde, right? So formaldehyde is the most unstable. It's the most reactive, because this positive carbon in the middle is very positive. The H's cannot help it out, and there's no way for this to become less positive. So it is the most reactive. So for two reasons, this is the most reactive. One, it's the most positive, so a nucleophile will sense it right away because it looks for positive. And two, there's no crowding. There's no steric issues. And so formaldehyde is the best, or the most reactive. It's the most unstable because it's the most reactive. Now, remember, when we deal with class 2, like let's say an ester or even a carboxylic acid, we'll use these two as examples, they both have resonance stabilization. So this carbon's positive, yeah, but this can go here and that can go up. So it has resonance. And notice that when you do resonance, what you're doing is you're pushing electrons towards the middle carbon. So this carbon is not so bad, right? It has electrons being pushed towards it through resonance. They have resonance stabilization. All class 2s have resonance stabilization. All class 2s. All class 2 have resonance stabilization. And remember that resonance stabilization is the most stabilizing feature. You can't get any better than that. So it's better than inductivity. It's better than hyperconjugation. So for that reason, we know if we wanted to organize a whole chart, formaldehyde is the most reactive, then aldehyde, because aldehyde has one carbon. So an aldehyde like this, it has inductive and it has hyperconjugation, right? So formaldehyde does not, but this has an R group, right? There's an R here. So that can give electrons through inductivity and hyperconjugation. Remember, the requirement for inductivity and hyperconjugation for a carbon is that it has a carbon neighbor. That's it. And so as long as there's a carbon attached to it,